Hey everybody, getting on to exponentials, and this is good stuff, and unfortunately, especially appropriate given things going on. But anyway, exponentials. You learned this last year in Algebra 1 class. What's the big idea with exponentials? Well, it's the base. So I'll write base down here. In particular, some base like y equals 2 to the x power, which would be, in this case, a doubling function. And this is why one of the applications of exponential growth, of course, is viruses, and we all know why that's important now. And then one person infects two people, or let's just say, let's keep it a little bit less, hitting a little bit less close to home, rabbits. Let's say we got two rabbits, then they have two babies, then they have four. They each have babies, then you have 8, and then they each have babies, then you have 16, and then they each have babies, then you have 32, and so forth. And therefore, with this kind of an exponential growth function, that's why if you remember flattening the curve on coronavirus, that's why it's really important. So we don't want the population growth to look like that. We want to flatten this thing out and not do that and kind of start to flatten that thing down that way. And that's why people get scared with any kind of a doubling function, which viruses are. Decay. Decay, well, let's go. Another growth. What are other growth things you remember from last year? Maybe compounded interest. And with compounded interest, we have a doubling function or some percent growth that we want to earn money on our money on our money. And that's why they say start investing for retirement early, because it gets big pretty fast if you start early and have lots of time to work over. Anyway, lots of things in the natural world can have this exponential growth, and then also decay. Decay is not quite as common. It's a base, but in this case it might be y equals 1/2 to the x, so it's half of half of half of half. Applications you remember from last year may include half-life. What is the half-life in particular of radioactive substances, and how long till half the radioactivity is there, and then another half of the half, and then half of the half of the half, and so forth. Another thing might be depreciation. Just like with compounded interest, your money is growing big faster with things like cars. They might be depreciating at a certain, how long till your car is half of its current value, and then half of that value, and then half of that value, sort of things like that. Okay, let's just go to see the picture. We'll come back up to here after we do the parent function. I think that's a little bit easier. So, well, what's a nice value for x? Let's always try 0. And when we try this, we know if we've got this parent function here, y equals 2 to the x, I guess I should call that y then. Anything to the 0 power is 1. And I've got this nice 0, 1 point here. And then, I don't know, what other kind of values of x that I should pick? 1. 2 to the 1 power is 2. And then 2 squared is 4, 3, 2 cubed is 8, 4. And then you can start to see it gets big much faster. 2 to the 4th is 16. And I'll go ahead and plot a couple of those points here. And 0, 1, and 1, 2, and 2, 4, and 3 goes, here's 5. 3, 8 goes to here, and then of course we're off the charts way up here somewhere. We've got that nice piece of the curve. And then when we go the other direction, if I try to go to the negative side, I'll do it in red just for the heck of it. If I go -1, 2 to the -1 is the same as 1 over 2. And, okay, so we're here. And then 2 to the negative, I don't know, I'll just say -3, which is 2 to the -3 means 1 over 2 cubed, which is 1 over 8. So it's really, really small right here. And that's why we go to an asymptote with an exponent. This is where you first experience an asymptote. What color should I make my asymptote? There's a horizontal asymptote here, HA, at y equals 0. Now, In the future, a couple things. I have a special name for this point right here. And it goes right here. You'll notice that's a nice, kind of like a vertex. The closest thing we've got an exponential to a vertex that can translate around. I call it an anchor point. And basically anything where my base is raised to a 0 power up here. I don't know, it's just nice to have a name for that so I can translate it around. I can't translate it perfectly, but you'll see. Okay, what's a domain? All real numbers. No reason I can't take any value of x and raise 2 to that power. What's the range? Well, it's got to be above the asymptote, the horizontal asymptote of y equals 0, so I can do my y is greater than 0, or I can do 0 to infinity, parentheses on both sides, one of those two ways. What's its shape? I don't know. I don't know, I guess you just say it's asymptote on one side to exponential growth. I don't know, there's no other way to say it. Intercepts. Well, do I have an x-intercept on this? Nope. None. Doesn't work. Y-intercept? Yes, definitely. That 0, 1, which in this point happens to be my anchor point. Okay, fine. As x goes to infinity, well, should say x goes to infinity, f of x, in this case it's really y since it's a y equal to the x function, but anyway, y goes to infinity. As x goes to negative infinity, f of x goes to 0, my asymptote on that one side. Increasing. Oh, remember the definition? Domain where I have a positive slope. Hope you haven't forgotten that one yet. The domain where I have a positive slope is all real numbers. And therefore, there's no negative slopes in this one. So null set. I'll use the null set thing. Okay, easy enough. Now, back to our HK translations. There are no translations on this one. This is the parent function by definition. So, starting point, anything to 0 power equals, well, we know that equals 1. And that is why I like the anchor point, because the base can be anything. It doesn't have to be 2 to the x. It could be 5 to the x. It could be 1/5 to the x. And anything raised to the 0 power will end up being 1 for y. So the anchor point is 0, 1 should stay as long as my as long as I'm raising my base to 0 power. The asymptote is y equals k. Notice that this plus k is going to shift the whole graph up, including the asymptote that goes with it, so that's obvious. And the translations for h also, they go right, left like they always do. K goes up, down like they always do. This really should have absolute value of a is greater than 1. Doesn't matter if it's positive or negative, it'll make it steeper. And if the absolute value of a is less than 1, it'll make it flatter and wider, regardless of whether it's positive or negative. Of course, if a is less than 1, then it flips it upside down. Okay, fine. Let's do another one. So in this one, note, I should have a translation that will shift my 2 to the 0 power to be at x is positive 4. So if I were to plug in 4, let's do that. 4 minus 4 is 0. So this whole thing then is 2 to the 0 power is 1. 1/2 times 1 is a half, plus 3 is 3.5. Notice, this is my anchor point now. And when I come over here, the next thing I want to look at is probably my asymptote, which comes from that plus 3 there, which is y equals 3. What color did I do asymptote? Oh, blue. I did my asymptote line in blue. So I should have a asymptote line at 3 right across here. My anchor point would be shifted to 4, 3.5, which is like right here. And I expect it to grow this direction and go to the asymptote to that side, because it's growth and not decay yet. We'll do decay in just a second. So if I want to be smart about my points, let's go back and look up at this one. Is there any reason to pick values to the left of my anchor point? Just say no, because it goes to the asymptote real quick. So to get my shape here, there's really no point in picking any value of x and wasting time plugging in 0, 1, 2, or 3. It's going to go to the asymptote really darn quick, unless I made a real bad mistake and didn't realize this was growth. Okay, so, I don't know, pick 5, 6, 7, 8. Points like that if you like. To get the real shape, it's still best just to plug them in rather than rely too much on these translations. Let me erase this for now. Okay, fine. 5 minus 4 would be 1. 2 to the 1 is 2 times, so that's 4. If I plug in 6 here, 2 squared is 4. Half of 4 is 2, so that's a 5. Notice I'm not using a calculator. This is easier just in your head. 7 minus 4 is 3. 2 cubed is 8. Half of 8 is 4 plus 3 is 7. And that's plenty of points. Really, just a few points are fine. So that's 5. That's 5 in the y. So 5, 4 is here. 6, 5. Yeah, wait. 5, 4 is there actually. 6, 5 is here. 7, 7 is here. And that's the shape of my curve. And that's good enough. Okay. Anchor point was this 4, 3 and 1/2. Translations. Yes, my H did what? It did a right 4. My K value did an up 3. My A value is 1/2, so that's a vertical shrink. Just like it is with parabolas and any other kind of shape. My domain, still all real numbers. My range, notice, is not impacted by anything but this vertical shift. So it is now 3 to infinity on the y value with parentheses. Certainly no x-intercept, call that null set. Is there a y-intercept on this one? Now that's interesting. What would I have to plug in for this? I would have to plug in 0, and 2 to the negative 4th, what was that, 1 over 16? Half of 1 over 16 was 1 over 32, so that's 3 and 1/32. Okay, fine. Anyway, it's really close to the asymptote. In behavior, once again, as x goes to infinity, f of x goes to infinity, negative infinity, it's going to the asymptote of 3. Increasing still, all real numbers, and null set. Okay, now let's take a turn and go to exponential decay. And by the way, if you want to pause this lesson, certainly do so at any time. And feel free to come back to it later. Exponential decay. Let's look at this one. Parent graph 1/2 to the x. What color should I do this one in? I'll do it in green. So we'll start off doing this as the y equals 1/2 to the x. I might use this grid for the other function in just a sec. Notice in this case, when I do 0, 1/2 to the 0 power, still 1. Still that exact same anchor point. Go away, little thing. There. Okay, fine. Now when I try 1 and 2, I get 1/2 and 1/4, and I say, hold on a sec. It's going to an asymptote, and that gets boring real fast. I'm not going to go that way anymore. I want to go try -1 and -2 and -4. And when I do that, 1/2 to the -1 is equal to 2 to the 1, which is 2. And to the -2, of course, 1/2 to the -2 will be equal to 2 to the +2, which is 4. And then this will be 16. Kind of the mirror image of what we had up here in our doubling function. So -1 is 2, -2 is 4. I skipped -3, but it'll be 8. Wait, there's 5. Here's 8. And then 16 will be off the charts. Notice it's a reflection across the line, the y-axis anyway. So, that being said, let's stop that and let's do the grid for, in purple, this function. Let's have some fun with it. What's the asymptote going to... Oh, this one's flipped. Notice. Translations. Before I get going, notice that I'm going to reflect over the x-axis this. Because the a value is negative, it's also going to be a vertical stretch. So it'll be steeper. And I have a horizontal shift that moves it left 4. And a k value of 5 that will move it up 5. So where should I start making this graph? Probably by starting with the asymptote of y equals 5. Because it's going to have an asymptote way up here. And then, what value will be my anchor point for this new purple function right here? Well, whatever value of x makes 1/2 be raised to the 0 power, which in this case will be x is negative 4. Let me think. Oh yeah, okay, sorry. I was confused with this negative 4 here. Notice, this is a new function. Don't worry about this negative 4. This is a new function. This is negative 4 for the purple function, not the green function. And so when I have a negative 4 here, negative 4 plus 4 is 0. 1/2 to 0 is 1. And then you get negative 2 plus 5, which is 3. Fine. And so if I do this, negative 4, 3 will be right here. And notice, I am still expecting this thing to go to the asymptote. Since it's decay, this is decay because it has a base less than 1, this 1/2 is less than 1, it should go to the asymptote on the right side, not the left side like Roth did. So I should be able to say the graph's going to go here. I don't need to pick any other points that are to the right of negative 4. I want to go more negative. I don't know, let's say negative 6 and negative 8 just for the heck of it. If I plug in negative 6, let's see, negative 6 plus 4 would be negative 2. 1/2 to the negative 2 would be 4. And negative 2 times 4 is negative 8 plus 5, which is negative 3. Ooh, that's going to go down there quick, isn't it? So that's going all the way down to here. Let's try them up. Negative 8. Make sure it holds the pattern. Negative 8 gets plugged into here. Negative 8 plus 4 is negative 4. So that should be the same as, I don't know, 1/2 to the negative 4 is equal to 2 to the 4th. So that's 16. And then 16 times negative 2 is negative 32 plus 5. Gee, what is that? Negative 27? So it's going way down here fast. So anyway, zoom. And that's my purple graph. Okay, fine. What was the anchor point? We said it was negative 4, positive 3. The domain, still all real numbers. The range, notice, comes up to a maximum since it's flipped. It goes from the negative y value of negative infinity up to a max at 5. Parentheses on everything. There is an x-intercept there. And do we have a way to get that? Well, gee, let's see. I want to solve this for when 0 is equal to negative 2 times 1/2 to the x plus 4 plus 5. Now, how to solve that? That's more interesting than you might think. It looks like it's at approximately equal to x approximately equal to, what would you say, negative 5, negative 6, somewhere around there. But this may stretch some of our solving skills at this point. Put this on hold in terms of getting an exact one. The y, did I plug in 0 yet? I did not. I think if I plug in 0, as I recall, I will get 5 minus 1/8. Check it if you want. What is that? 4 7/8. And behavior. As well, once again, as x approaches infinity, f of x approaches my asymptote at 5. And as x goes negative infinity, f of x goes down to negative infinity there. Increasing, never. This one always has a negative slope. No, wait, this one always has a positive slope. What did I say about this one? Oh, that's a positive slope. Hey, that's also a positive slope. Interesting, isn't it? Increasing is all real numbers. It's because my decay's been flipped. That's why. A little bit opposite of what I was thinking. Decreasing, never. And there you go. Okay. Wow, this has been a pretty long video already. I think I'm going to take a quick break, and then maybe I'll do a second video for the word problems down here, the applications, and do a few of those in a second one. So these videos aren't too long in one stretch. Okay. We'll skip this, and I think if you've listened up to now, you got the idea.